Hello, Math Scholars. Professor McMath here, and we got a good one for you today. Solving rational equations. This one's going to get a little interesting. You may not like parts of this, but that's okay. We persevere through the tough challenges. So a rational equation is exactly as it suggests. We have our rational fraction algebraic functions, and we want to solve them as equations. So, fractions. Yay, everyone's favorite thing to work with. Well, the idea behind solving fractions is to get a common denominator. Now, if there's only one spot where the variable exists, you probably want to get a common denominator with the other fractions. So then you can possibly get them all to one side. So 5 over 6 with an 18, I can make this 15 over 18 by multiplying top and bottom by 3. This now allows me to subtract that over, and we'll have 4 over x plus 3 on the left-hand side equals 23 minus 15 is 8, and then over 18. Which reduces to 4/9. Now, normally from here we would go ahead and just simply cross multiply and solve this out. However, one particular thing that happens here, and I'll show you it works both ways, is actually let me show you cross multiplying first. So we cross multiply. 4 times 9 is 36. 4 times x is 4x. 4 times 3 is 12. Subtract the 12 over to get 24 equals 4x, which means x is 6. We always have to make sure we plug it back in and recognize that right here, this tells us x cannot equal negative 3. So if we had negative 3 for an answer, then we wouldn't be allowed to use it. Now, back to our fraction. We had 4 over x plus 3 equals 4 over 9. We cross multiplied. But if we recognize that both numerators are the exact same numbers, they're both 4s. Well, that tells me then for these two fractions to be equal, then that means their two denominators must be the exact same numbers. Which means x plus 3 has to equal 9. Well, if we subtract 3 over, we get x equal to 6, which is the exact same thing we found over here. So, if you are lucky enough to find that your numerators or denominators are both the exact same numbers or expressions, you can ignore them and just set the other parts equal to each other then. Alright, so x equals 6. Now, if the entire thing is algebraic, well then we need to factor everything first to recognize some common denominators. So we would have 2x over x plus 5 minus, we only want to factor the denominators, we want to ignore the numerators. X squared minus x minus 10 over, this factors x plus 3 and x plus 5. So the first thing we want to recognize is the fact that x cannot equal negative 3 or negative 5. Because if they equaled any one of those expressions, we would have 0 in our denominators, and that's not allowed. Now, common denominators. Well, we should recognize that if we have an x plus 5 here, an x plus 5 and an x plus 3, and this has an x plus 3 here, x plus 5 times x plus 3 is my common denominator. So since I already have an x plus 5, we're going to have to multiply this one by x plus 3. So it's 2x times x plus 3. And again, we have it over as x plus 5, x plus 3. Minus, we don't need to worry about this one. It's still just x plus 5 and x plus 3. And then equals, this now gets multiplied by the x plus 5. And again, it has the x plus 5 and x plus 3. Now remember in the previous video we talked about that if all our denominators were the same, the numerators are equal, or vice versa. That's what's happening right here. We notice all our denominators are the same. So essentially, you don't really care about them then. So all that's left is just worrying about the numerators, which would be when we distribute 2x squared plus 6x. Since this is subtracting the entire expression, I need to distribute the negative to the whole expression. Get negative x squared plus x plus 10 equals our 3x plus 15. Well, we recognize an x squared here, which means it's a quadratic, which means it needs to equal 0. So we'll combine like terms and move the 3x plus 15 over. We will get x squared, and then we will get plus 4x, and minus 5 equal to 0. So when we factor that, we'll get x plus 5 and x minus 1, which will give us solutions of negative 5 and positive 1. Which we already know that negative 5 cannot work because it was said not to equal that in the very beginning. So our only solution is x equals 1. Alright, so that's the idea behind solving these algebraic, these rational functions. You want to get a common denominator, meaning factor every single denominator as far as possible, and just multiply the other fractions by the missing denominator piece. Once you do that, you only need to care about the numerators, because all the denominators will be the same, so they will cancel out. If you are subtracting a numerator, then make sure you subtract the entire expression and change all of its signs. Alright, so let's do that again. So we have 2 over z plus 1 minus 1 over z minus 1 equals negative 2 over z squared minus 1. So I can't really factor this. So we still have 2 over z plus 1 minus 1 over z minus 1 equals negative 2, but I can factor this one. Z plus 1 and z minus 1. So this tells us that z cannot equal plus or minus 1. Well, I need a z plus 1 and a z minus 1 in all expressions. I only have a z plus 1, so it'll be 2 times z minus 1. I have the z minus 1, so I'll need a z plus 1. And this already has that. Again, remembering, the numerators are the only thing that's going to matter left over. The denominators will cancel out. So, when we go through this, we'll get 2z minus 2 minus z minus 1 equals negative 2. Well, we have a linear equation, so we need to combine like terms. 2z minus z is just simply z. Negative 2 minus 1 is negative 3. When I add the 3 to both sides, we'll get z equal to positive 1. But the problem is, we were told in the very beginning that z cannot equal plus or minus 1. So that can't work. Well, that was our only solution. The previous example was a quadratic, which had multiple solutions. Here, this is the only one. Well, if nothing works, then there is no solution. We're done. Okay, so those are the straightforward equations you'll need to work through and solve. There's also 3 different types of word problems you're going to need to deal with. First one, how many milliliters of a 13% saline solution must be mixed with a 7 milliliters of a 52% saline solution to make 34% solution? Okay, well, how the heck are we going to figure this out? Well, here's the way we want to deal with this. This is generally the most efficient way to deal with it. We're going to set up this kind of proportion. Our percent, that's concerning. Well, give me a second. Alright, should be working now. So you're going to do percent over 100. Percent of the solution you want to create over 100. That's going to equal, well, the amount of the saline, I guess, in this case. It's not always going to be saline. The amount of the product, I guess, maybe. So we'll do product versus the total solution. This is the one kind of percent we want to set up every single time. This simple proportion. Percent over 100 for the percent that we're trying to create. And the amount of the product, in this case saline, will be up top. And the total solution will be on the bottom. So here's how it works. First fraction is 34 over 100. Very straightforward. Second fraction. Well, we have 7 milliliters of 52% solution. So what we'll do is we'll do 52 times 7. Plus, well, we have 13% of an unknown number, which would mean it's x. Because we don't know how many milliliters this seconds of this 13% solution is going to go in there. That's our product. Now on the bottom, well, there were 7 milliliters total solution, added to, again, an unknown milliliters of the new solution. So it'll be 7 plus x on the bottom. And this is what we want to try and solve. Now, this is where it gets fun. So we're going to cross multiply. Normally I would reduce the fraction 34 over 100, but because we're dealing with percents, 52% times 100, it kind of like cancels out the decimal, so I don't really necessarily want to do that. So again, we're just going to cross multiply. We're going to get 238, that's a 7 times 34, plus 34x, equals, if I do 0.52 times 7 times 100, it's the same thing as 52 times 7, because 100 will cancel with the 0.52. And that'll leave us 364. And 100 times 0.13 is just 13, so plus 13x. So now we have a very straightforward equation to solve. I'll move the 13x over, we get 21x. I'll move the 238 over, get 126. And if I divide by 21, x is equal to 6. So it'll be 6 milliliters is what we're looking for. Okay, so problems involving percentages like this. It's a mixture problem. This is how you want to solve it out. So you're doing the percent over 100 equals the product we're dealing with, which is always going to be the percents themselves, multiply how much there is, divided by the total amount, which is just the 7 plus x in this case. You'll probably see similar stuff in chemistry already. If not already yet, then you'll see it soon. Alright, so that's your mixtures. We also deal with our time and distance. So Amanda drove to the town hall and back. It took 1 hour less time to get there than to get back. Average speed of the trip was 80 miles per hour. Average speed of the way back was 60 miles per hour. How many hours did the trip take? Okay, not quite sure what this town hall is if we're talking about it's an hour less time to get there than it did to get back or traveling at these kind of speeds. Clearly it's not in the same town she's living in, but let's just not worry about that. Let's not worry about realistic word problems. So the idea here is dealing with the fact that distance equals... Again? Sorry. I'm not 100% sure why the pen just keeps on crapping out on me like that, but anyway, we're dealing with the idea of distance equals rate times time. Now the reason why this is important is because in this particular scenario, our distances are the same. You're going there and back, so therefore your distance is not changing. So what we're going to say essentially is then the distance there, d1, has to equal the distance back, d2. So that means rate 1, t1, has to equal rate 2, t2. Now, it says average speed there was 80 miles per hour. That's our rate 1. Average speed back was 60 miles per hour. That's our rate 2. Now I've got to deal with our times. Well, it says it takes 1 hour less time to get there than it did to get back. So if time getting back is, we'll call it x, that means getting there was x minus 1. We also could have easily called this x and then made this x plus 1. Just the same idea. So, well, now we have a variable, only one of them we can actually distribute and solve. So we get 80x minus 80 equals 60x. When I rearrange things, we'll get 20x equal to 80. And therefore, x equal to 4. Which means it will take 4 hours to get back, 3 hours to get there. Because that's how many hours did the trip take to get there. How many hours did the trip there take? Yeah, okay, whatever. Okay, so the idea behind that is that one right there. So it could be a situation where the distances are the same, maybe the times are the same, distance are different, or maybe the times are related to each other, and you got to work with distance some other way. Either case, you're always going to work with d equals rt. Maybe it will be r equals d over t, or t equals d over r, some other way like that. Pretty much you're dealing with your variation formulas that we just talked about. So that's your time and distance. Last one is the idea of working together. So it takes Alberto 13 hours to pick 40 bushels of apples. Pranav can pick the same amount in 14 hours. How long will it take them if they work together? Very straightforward problem. Here's how we do it. 1 over 13 plus 1 over 14 equals 1 over x. Because what's happening is, here's what we're doing is that 1 over 13. If it takes 13 hours to pick all 40 bushels, that means in 1 hour, he can do 1/13 of the labor. Pranav can do 1/14 of the labor in 1 hour. So combined, we want to see one of what part, how long it would take him. Like, for example, if x was 5, that means it would be combined, it takes them 5 hours to do everything, so you can do 1/5 of it in 1 hour. That's the whole idea behind how we're setting up this equation. It's always 1 over the total time plus 1 over the total time equals 1 over x to see how long it would take them to work together. Well, to solve this out, we need to multiply everything by the denominators, 13, 14, and x. So if I multiply 13 by this, it cancels leaving just 14x. Multiply 14, cancel leaving just 13x. If I multiply the x, it just leaves 13 times 14, which is 182. So when we combine, we'll get 27x equals 182. Divide by 27, x is not a whole number, it's not a nice number. It is 182 divided by 27. It is 6.7407 hours. So it's going to take them somewhere in between it's going to be about 6 3/4 hours. So 6 hours and 45 minutes, roughly, if they were to work together. That's a lot of work. Not gonna lie about that. But hey, if you're doing takes you 13 hours to do it by yourself, 14 hours to do it by yourself, is not too bad. Alright, so these are the 3 different word problem types you're going to see with these rational equations. Make sure you understand how to do each type. Mixture problems, distance problems, and then working together problems. These are the 3 you're going to see. Alright, that's all I got for you today. Again, I appreciate you guys watching. It's been a pleasure, and that means McMath is out now.